Hello friends, welcome to my lecture on tautologies and contradictions. First let us define what do we mean by a tautology. A formula is said to be a tautology. Tautology is also known as self-evident if it is true for every assignment of the truth values to its compound statements. A tautology can be thought of as a rule of logic. The opposite of a tautology is a contradiction, and contradiction means evidently false. So, the opposite of a tautology is a contradiction which is always false. In other words, a formula is called a contradiction if every truth assignment to its components results in the formula being false. Consider the propositions: the professor is either a woman or a man. The next proposition: people either like watching TVs or they do not. Now, you can see these two propositions are both always true, and so they are called tautologies. Now, let us consider the propositions: x is a prime and x is an even integer greater than 8. The next proposition: all men are good and all men are bad. Such propositions are always false and therefore are called contradictions. The following propositions, let us look at the propositions P or not P, not P and Q or Q, P implies P or Q. Okay. These propositions are all tautologies. We can check that by writing their truth table. So, let us write the truth table for the first proposition P or not P. Okay. So, P has truth values T and F, not P will have the corresponding truth values as F and T, and therefore, P or not P will have the truth value T in the case when P has truth value T and not P has truth value F, and then in the case when P has truth value F, not P has truth value T, then again P or not P will have truth value T. So, P or not P has truth values T for all the possibilities here, and therefore, we say that P or not P is a tautology. Let us take the second proposition not P or Q, not P and Q or Q, and let us form the truth table. So, first we form the truth table here for the case P and Q. Okay. P and Q have truth values T T, T F, F T, F F, and when P and Q are both T, P and Q will have truth value T. For the case T F, when P has truth value T, Q has truth value F, P and Q will have truth value F, and similarly for the other cases P has truth value F, Q has truth value T, P and Q will have truth value F, and when P has truth value F, Q has truth value F, P and Q has truth value F. Then negation of P and Q will have truth values F, T, T, T. Okay. Now, negation of P and Q or Q will then have the truth values. So, let us consider negation of P and Q is this and R Q. So, Q has truth value F. So, when negation of P and Q has truth value F and Q has truth value T, then negation of P and Q or Q will have truth value T. And similarly, for the case when negation of P and Q has truth value T and Q has truth value F, the negation of P and Q or Q will have truth value T. And when both have truth values T, okay, the negation of P and Q or Q will have truth value T, and when negation of P and Q has truth value T and Q has truth value F, the negation of P and Q or Q will have truth value T. So, you can see the column of the truth values for negation of P and Q or Q has all T's, and therefore, it is a tautology. Now, let us consider the third case. In the third case, we have to show that P implies P or Q is a tautology. So, these are the truth values of P and Q T T, T F, F T, F F, then P or Q has truth values T T, T F, and then P implies P or Q. Okay. So, P implies P or Q means T, when P is T and P or Q is T, P implies P or Q has truth value T, and again here P has truth value T, here this has truth value T. So, it is T, and when P has truth value F, P or Q has truth value T, then P implies P or Q has truth value T, and when P has truth value F, PRQ has truth value f, then P implies PRQ has truth value T. So, again in the column for the proposition P implies PRQ, all the values, truth values are T, therefore, it is a tautology. Now, let us look at the propositions P or Q and not P. P or not P implies Q or not Q. We will see that both of them are contradictions. That means, the column corresponding to these propositions will have all truth values f. PQ has truth values TT, TF, FT, FF, these are the combinations. Now, then not P has truth values FF, TT. Now, Q and not P, Q and not P will have truth values for TF it will be F, for FF it is F, for TT it is T, for FT it is F, and then P and Q and not P, okay. P and Q and not P. So, it is T here, it is F here. So, we have F, here it is T, here it is F. So, this is F, and then F and T gives F, and F gives F. So, the column corresponding to the proposition P and Q and not P has F, okay, throughout for all possible combinations, and therefore, it is a contradiction. Now, let us go to the second proposition P or not P implies Q or not Q. So, the truth table let us form here again. So, P has truth values T and F, the not P has truth values F, T, P and P or not P, okay. P or not P will then have truth values T here, F here. So, it will give you T, F and T here. So, it will give you T, and Q has truth values T and F, not Q has truth value F and T. So, Q and not Q will have truth values F here, and this is also F, and therefore, now let us see P or not P has truth value T, Q and not Q has truth value F. So, when it is T here, it is F here, we have F in the case of this implies implication, and then P and or not P has truth value T, Q and not Q has truth value F. So, again we have F. So, the column corresponding to the proposition P or not P implies Q and not Q has F for all possibilities here. So, it is a contradiction. Now, there are infinite number of tautologies we shall see. First, let us see the proposition P or not P is a tautology, and the proposition P and not P is a contradiction. So, you can see here P or not P. So, P is having truth values T F, not P has truth values F and T. So, P or not P will then have truth value T, and here also T, and therefore, it is a P or not P is a tautology. In the case of the other situation P or and not P, okay. So, P has truth value T F, not P has truth value F T, then P and not P will have truth value F for the case T F, and for the case F T also it is F, and therefore, P and not P is a contradiction. Now, we have a theorem which is very useful theorem. If PQ is a tautology, then negation of PQ is a contradiction, and conversely, okay. So, this can be easily proved, since a tautology we have seen that all the truth values, okay, in the case of a tautology are T, okay. So, since a tautology is always true, the negation of a tautology will give you false, okay. So, the negation of a tautology will give all values false, that means negation of tautology is a contradiction, okay. So, and conversely, if we consider the negation of PQ, okay, which is a contradiction, then P will be a tautology, because negation of P, if it is a contradiction, that means all values in the column corresponding to the contradiction, all values will be false, and therefore, PQ, okay, PPQ will be a tautology, okay. So, this theorem now can be used this can be used later. So, let us do another theorem, principle of substitution. Suppose PQ is a tautology, then P1, P2 and so on is a tautology for any propositions P1, P2. Since PQ does not depend upon the, we have seen that PQ does not depend on the particular truth values of its variables PQ. It is always T in the column for a tautology. Okay. So, it does not depend on the particular truth values of its variables p q. Therefore, we can substitute p 1 for p, p 2 for q and so on in the tautology p, p q and so on, and still have a tautology. Let us say for example, this proposition p and not p, okay, or not p and not q. Okay. We shall see that it is a tautology. So, you can see here I call this this as p. Okay. Let us define p to be let us take p to be p and not q. Okay. Then the given proposition is of the form p or not p. Okay. Now, we have just now seen p or not p is a tautology. Let us go to that place where we proved that p or not p. Okay. You can see here we have proved that p or not p is a tautology. Okay. So, we have just now shown that p or not p is a tautology. Therefore, by the principle of substitution, okay, let us put the value of p. The value of p is p and not q. Okay. So, p and not q or not p and not q is also a tautology. So, we can see that the principle of substitution is very useful here, just by using the fact that p or not p is a tautology, we can decide about the given proposition that it is a tautology. The propositions p, p q and so on and q, p q and so on are logically equivalent if and only if the propositions proposition p, p q implies and implied by q, p q is a tautology. Okay. So, that is why we said that there are infinite number of tautologies. All logically equivalent propositions give us tautologies. So, suppose p, p q is logically equivalent to q, p q, then the propositions p, p q and q, p q have same truth table. This we have seen when we defined the logically equivalent propositions. So, when two propositions are logically equivalent, their truth tables are same. Hence, the proposition p, p q if and only if q, p q is true for any values of the variables p q, because when p, p q and q, p q have the same truth table, then the proposition p, p q implies and implied by q, p q will have t all t's in its column. Okay. So, the proposition is a tautology, and conversely if p, p q implies and implied by q, p q is a tautology, then p, p q and q, p q will have the same truth values, because p, p q and q, p q if they do not have the same truth values, then p, p q and q, p q cannot be p, p q will not imply and implied by q, p q, because they it is a sorry, if p, p q and implies and implied by q, p q is a tautology, then p, p q and q, p q will have same truth values, because this is a tautology. So, here we will have a t in the all values will be truth values will be t here, and therefore, p, p q and q, p q should have same truth values, and therefore, they are logically equivalent. Let us consider the example not p and p or q implies q. Okay. So, let us show that it is a tautology.
नमस्कार सर.
No, तो सर 5 मिनट लगेंगे. So, let us form the truth table for this. So, p q have truth values t, t, t f, f t, f f. Okay. Then not p has truth values f, f, t, t. Okay. Now P and Q, P R Q, let us write the truth values for P R Q. So P R Q, when P and Q both have T, P R Q has T, T and F gives you T, F T gives you T, F F gives you F. Okay. Then not P and P R Q. Okay. So not P and P R Q. So not P has truth value F, P R Q has truth value T. So we have F here, and then it is F, this is T. So again we have F, then this is T, this is T. So we have T here, we have T here, here F. So we have F here. Okay. Now not P and P R Q implies Q. Okay. So let us look at this column. Here we have F and here we have T. Okay. So we have T here, here we have F, here we have F. So we have T here, here we have T, here we have T. So this proposition gives the truth value T, and then we have F here and here we have F. Okay. So we get T here. So you can see the column corresponding to the proposition not P and P R Q implies Q has truth value T for all combinations here, and therefore not P and P R Q implies Q is a tautology. Now let us take an example on contradiction. So let us consider the example P implies and implied by Q, P implies and implied by Q and not P and Q. Okay. P implies and implied by Q and not P and Q. We have to show that it is a contradiction. So we have to show it is a contradiction. Okay. Let us write its truth table. So P Q not P and Q, then P implies and implied by Q is logically equivalent to P implies Q and Q implies P. Okay. So we have to write the truth values of P implies and implied by Q by finding the truth values for P implies Q and Q implies P, and then we consider lastly P implies and implied by Q and not P and Q. Okay. We must have truth values F here, okay, for all combinations. So P Q have truth values T, 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 F, F, T, F, F. Okay. Then not P has truth value F, F, we have T here, we have T here. Now not P and Q, not P and Q will have truth value F, will have truth value F, will have truth value T, and will have truth value F. Okay. Now P implies and implied by Q is logically equivalent to P implies Q and Q implies P. So let us find the truth value for P implies Q. So P implies Q, okay, T T, okay, gives T here, then T F, T F gives F here, then F T gives T, okay, then F F gives T, then Q implies P. Okay. So Q implies P, T T gives T, then F T gives T, then T F gives F, okay, and then F F gives T. Now P implies Q and Q implies P. We have to consider P implies Q and Q implies P. Okay. So T T T, F T F, then T F F, and then T T T. Okay. So we get T F F T. Okay. Now P implies Q, and P implies and implied by Q and not P and Q. Okay. So, let us consider this column and this column. Okay. So, T here, F here gives F here, F gives F, okay, F T gives F, and then T F gives F. So, you can see in the column corresponding to the proposition P implies and implied by Q and not P and Q has all truth values F, okay, and therefore, we can say that P implies and implied by Q and not P and Q is a contradiction. So, that gives the solution of this example. Thank you very much.